What does a ghost look like? It is a question that has haunted us, not just in folklore, but in the grandest theatre of all the cosmos itself. For centuries, we have told ourselves stories of apparitions, of entities that exist by their absence, defined only by the chill they leave in the air, or the shadow they cast in the periphery of our vision. But out there adrift in the unimaginable voids between the stars are ghosts of a far more profound and terrifying nature. They are the universe's ultimate monsters, born from the collapse of colossal stars, and they possess a power so absolute, a hunger so complete, that they have torn a hole in the very fabric of reality. We call them black holes, and their defining feature, the very essence of their being, is that they cannot be seen. They are perfect blackness, an utter and total absence of light in a universe that is otherwise ablaze with the fires of 100 billion galaxies. So, the question becomes a paradox, one that has taunted astronomers for generations. How do you photograph a ghost? How do you capture an image of an object whose entire identity is built upon being invisible? This is not a story about pointing a telescope at a distant star. It is the story of an impossible quest, a multi-generational human endeavour to stare into the deepest abyss imaginable and force it to yield a portrait. It is the story of how we, a species confined to a fragile blue marble, decided to build an eye the size of a planet, not to look at the light but to chart the precise shape of the darkness. The idea of such an object is not a modern invention born from the complexities of 21st century physics. It is a seed of thought planted over 200 years ago, long before we even knew the true scale of our own galaxy. In 1783, a British natural philosopher named John Michell, a quiet and brilliant man, engaged in a stunning thought experiment. He knew that gravity affected everything, and he knew from the work of Isaac Newton that light could be thought of as a particle, a corpuscle. So he reasoned, if you had a star that was sufficiently massive and dense, could its gravitational pull become so strong that even a particle of light, moving at the fastest speed possible, could not escape its surface? He imagined light, particles being fired from the star only to be dragged back down by an overwhelming gravitational grip like a stone thrown into the air on Earth. Michell called these hypothetical objects dark stars. They would be out there, he speculated, massive and powerful, yet utterly invisible to our telescopes, detectable only by the gravitational influence they exerted on the luminous companions they held in their sway. It was a staggering, almost Gothic piece of intuition, a ghost in the celestial machine. A decade later, the great French mathematician Pierre-Simon Laplace independently arrived at the very same conclusion, solidifying the idea as a serious, if unsettling possibility within the framework of classical physics. Yet, for over a century, the concept remained a fringe curiosity, a piece of mathematical speculation that was too strange, too far outside our experience to be fully embraced. It was a monster that slumbered in the margins of scientific textbooks. Then, in the early 20th century, a revolution occurred that would shake the foundations of our understanding of the universe. Albert Einstein, with his theory of general relativity, rewrote the laws of gravity. He told us that gravity was not a force pulling objects together, but rather a curvature, a warping of the very geometry of space-time itself. Massive objects, he showed, don't pull on planets. They create deep valleys in the fabric of reality, and planets simply follow the curves. It was a vision of the cosmos as a dynamic, malleable tapestry, and within the elegant mathematics of his field equations, the old ghost of the dark star awoke, now transformed into something far more bizarre and far more powerful. Just months after Einstein published his theory, a German physicist named Karl Schwarzschild, working from the trenches of the First World War, found the first exact solution to Einstein's equations. His solution described the space-time geometry around a single, non-rotating spherical mass. But buried deep within his mathematics was a terrifying feature, a point of infinite density and zero volume where the laws of physics seemed to break down entirely a singularity. Surrounding this singularity, his solution predicted a boundary, a one-way membrane from which nothing, not even light, could escape. Einstein himself was deeply disturbed by this implication. He believed it was a mathematical monstrosity, a flaw in the theory that nature would surely find a way to avoid. For decades, he and many other leading physicists resisted the idea, viewing the singularity and its inescapable boundary as a mathematical fiction, not a physical reality. How could nature permit such an absurdity? How could a star, a beacon of light and energy, crush itself down into a point of infinite nothingness, taking a piece of the universe with it? The resistance was understandable. The concept assaults our intuition. We are creatures of a world governed by escape. We can climb out of a valley, launch a rocket from a planet, or swim against a current. But what Schwarzschild's mathematics described was a point of absolute finality. This boundary is what we now call the event horizon. It is not a physical surface you could touch. It is a threshold in space-time itself. Imagine a wide, placid river that gradually quickens, flowing towards a colossal waterfall. Far upstream, a skilled swimmer can easily move against the current, but as they get closer, the water's speed increases. There is a line, a precise and unforgiving point in the river, where the water is flowing faster than the strongest swimmer could ever hope to swim. Once you cross that line, no amount of effort can save you. Your fate is sealed. The waterfall is inevitable. The event horizon is precisely this line for the cosmos, but the current is the inward pull of warped space-time, and the waterfall is the singularity at the center. Outside the event horizon, escape is still possible, if difficult. But the instant you cross it, the geometry of space-time itself is flowing inward faster than the speed of light. Since nothing can travel faster than light, escape becomes a physical impossibility. The future for anything that crosses the horizon is a single point, the singularity. Even light, the fastest thing in the universe, is caught in this inexorable current and dragged down into oblivion. This is the source of the black hole's invisibility. It is not just dark, it is the source of a profound and perfect darkness. It is a cosmic dead end, a place where information is erased and the familiar laws of cause and effect cease to apply. It is a scar on the face of the cosmos, a one-way trip to the end of physics as we know it. So if the object itself is a perfect void, a hole in the universe, what is there to photograph? The challenge seemed insurmountable for decades. A black hole by its very nature emits no light, no radio waves, no information of its own. It is a silent black silhouette against the black backdrop of space. But what if the backdrop wasn't black? What if you could place a fantastically bright screen times behind times the black hole? This is the key, the theoretical breakthrough that transformed the quest from a fool's errand into a tangible, albeit monumental scientific goal. Fortunately, the universe provides its own cosmic screen. Many black holes are not isolated in the void. They are ferocious engines of consumption surrounded by vast, swirling whirlpools of gas, dust, and shredded stars. This material caught in the black hole's immense gravitational grasp doesn't fall straight in. Instead, it forms a structure called an accretion disk, a cosmic traffic jam of matter spiraling inward towards its doom. As this material gets closer to the event horizon, it is accelerated to nearly the speed of light. The friction and compression within this disk are so extreme that it heats up to billions of degrees, glowing with an intensity that can outshine entire galaxies. This accretion disk is the celestial blowtorch, the ultimate cosmic searchlight. It is the bright screen we needed. A black hole situated in front of this inferno of light would in theory cast a shadow. We wouldn't be seeing the black hole itself, but its silhouette, its negative image, carved out of the brilliant light behind it. But the image wouldn't be a simple, clean circle. The black hole's gravity is so extreme that it acts as a powerful gravitational lens, distorting the path of light that passes near it. Light from the part of the accretion disk that is directly behind the black hole would be bent up, over, down, and under the event horizon, creating a luminous ring of light that appears to encircle the central darkness. This feature, predicted by Einstein's theory, is known as the photon ring, or the last orbit of light. It's a halo made of light that has been forced to skirt the very edge of oblivion before making its escape towards our telescopes. The final image, therefore, would be a combination of two things: a dark central region, the shadow, which is larger than the event horizon itself, and this brilliant warped ring of light framing the abyss. To capture this image, this shadow and its halo would be to do more than just see a black hole. It would be a direct visual confirmation of Einstein's theory of general relativity in the most extreme environment the universe has to offer. It would be a way to measure the monster to determine its mass and perhaps even its spin by the precise size and shape of the shadow it casts. It would be turning a century of abstract mathematics, of mind-bending thought experiments, into a tangible, observable reality. It would be photographing the curvature of space-time. The dream was magnificent, but the reality of the challenge was crushing. The largest supermassive black holes in our cosmic neighborhood, Sagittarius A, times at the heart of our own Milky Way, and the Leviathan in the galaxy, Messier 87, are astronomically far away. Despite their immense mass, their apparent size in our sky is infinitesimal. Trying to resolve the event horizon of M87's black hole is famously the equivalent of trying to photograph a single donut sitting on the surface of the moon. No single telescope built or even conceived could ever possess that kind of resolving power. The laws of optics dictate that to see smaller details you need a bigger lens, a wider dish. To see a donut on the moon would require a telescope, not meters or even hundreds of meters across. It would require a telescope nearly the size of the Earth itself. And that is precisely the audacious, seemingly impossible solution that a global community of scientists and engineers devised. They would not build a single planet-sized dish. Instead, they would use a technique called very long baseline interferometry. They would link together radio telescopes scattered across the entire globe, from the high deserts of Chile to the volcanic peaks of Hawaii, from the mountains of Spain to the frozen plains of the South Pole. They would synchronize these disparate observatories with atomic clocks of unimaginable precision, recording the faint radio waves emanating from the accretion disks of their targets simultaneously. Then, through the magic of supercomputing, they would combine these torrents of data, trillions of bytes of information, effectively stitching them together to synthesize a single virtual telescope with an aperture as wide as our planet. They called it the Event Horizon Telescope. It is one of the most ambitious and complex scientific instruments ever created, a planetary eye turned towards the deepest mysteries of space and time. This is the story of that instrument, of the people who built it, and of the profound moment when, after decades of dreaming, humanity finally peered into the abyss and captured a picture of the ghost that haunts our universe. It began not with a telescope but with a piece of paper, not in a silent, sterile observatory but in the frozen mud and chaos of the Great War. On the Eastern Front in 1915, a German artillery officer and brilliant physicist named Karl Schwarzschild found himself with a moment of quiet reprieve from the thunder of guns. In his hands, he held the freshly printed words of Albert Einstein, a revolutionary new theory of gravity called general relativity. For centuries, we had imagined gravity as a force, an invisible rope pulling objects toward one another, a concept handed down to us by Isaac Newton. But Einstein offered a vision far more profound, far more elegant. He asked you to stop thinking of space as an empty stage on which the cosmic drama unfolds. Instead, he revealed that space and time are the drama itself. They are a single, unified fabric spacetime, a dynamic, pliable medium that can be warped, bent, and distorted by the presence of mass and energy. Imagine a vast, tightly stretched cosmic trampoline. A bowling ball placed in its center creates a deep well. A marble rolled nearby no longer travels in a straight line. It follows the curve spiraling inward. To that marble, it feels an inexorable pull. That feeling, that path dictated by the curve, is what we call gravity. This was Einstein's radical revelation. Matter tells spacetime how to curve, and the curvature of spacetime tells matter how to move. It was a complete rewriting of the very grammar of existence, a set of 10 beautiful, intricate equations that promised to describe the grand waltz of the cosmos, from the fall of an apple to the orbits of distant galaxies. Einstein believed his theory painted a picture of a graceful, orderly universe, a clockwork of celestial bodies moving along predictable paths carved into the geometry of reality. He was a man who craved harmony in the cosmos. So certain was he of this cosmic balance, he even added a special term to his equations, the cosmological constant, a kind of universal anti-gravity, designed to prevent the universe from collapsing under its own weight, ensuring a majestic, static, and eternal stage. The universe, he felt, should be stable, it should be sensible, it should not contain monsters. But back in the trenches amidst the bitter cold and echoing artillery, Karl Schwarzschild was about to discover a monster lurking deep within the pristine logic of Einstein's mathematics. He decided to test the new theory on the simplest possible case, a single, perfect, non-rotating sphere of mass, like an idealized star floating alone in the void. He was seeking the first exact solution to Einstein's field equations, a clean, perfect test of this new cosmic language. And with breathtaking speed he found one. He sent his calculations to Einstein, who was stunned by the elegance and rapidity of the work. Schwarzschild's solution showed that at a great distance, Einstein's gravity behaved exactly as Newton's did. This was a triumph. The new theory contained the old, a crucial test for any scientific revolution. But as Schwarzschild pushed his mathematical probe closer and closer to the center of this imaginary star, the beautiful equations began to whisper of something terrible. They began to break down. They began to scream. The equations revealed that for any given amount of mass, there exists a critical threshold, a point of no return. If you could somehow squeeze all the matter of our sun down into a sphere just 6 kilometers across, or the entire Earth into the size of a sugar cube, something extraordinary and terrifying would happen. At this boundary, which we now call the Schwarzschild radius, the gravitational pull becomes so overwhelming, so pathologically powerful, that reality itself is warped beyond recognition. It was a line drawn in the sand by mathematics itself, a border beyond which the universe as we know it ceases to exist. At this radius, the equations predicted that the curvature of space-time becomes infinite. Time for an observer watching from the outside would appear to slow down for an object falling inward, stretching out longer and longer as it approached the edge. Its light would be pulled into lower and lower frequencies, reddening until it faded completely from view as if the universe itself were holding its breath. The object would seem to freeze for all eternity at this invisible precipice, a ghost ship forever stranded on a cosmic shore. The equations seemed to be yielding gibberish, a mathematical fever dream that had no place in the physical world. Surely Schwarzschild and Einstein thought this was just a flaw, a sign that the theory was being pushed beyond its limits. Nature, they reasoned, would never allow such an absurdity. Yet the mathematics was relentless. It prophesied not just one but two distinct points of cosmic madness. The first was this boundary, this surface of infinite redshift. We call it the event horizon. It's not a physical wall you could touch or see. It is far stranger than that. It is a one-way door in space-time. Imagine it as a cosmic waterfall, a river of space itself flowing inward toward the center. Far away the current is gentle, and you can easily swim against it. But as you get closer, the current gets stronger. The event horizon is the point where the speed of that inward-flowing river of space exceeds the speed of light. At that moment, no matter how powerful your rocket, no matter which direction you face, you are carried inward. Everything is carried inward. Even light, the fastest thing in the universe, is dragged down into the abyss. Nothing that crosses this threshold can ever report back. No information, no message, no glimmer of light can ever escape. It is the ultimate prison wall forged from warped geometry, and the secrets it holds are kept for eternity. For the unfortunate traveller falling through the passage across this boundary would be utterly unremarkable, a smooth, silent transition into the unknown. But for us, the viewers left behind, they would be gone forever, erased from the visible universe. This was horrifying enough. But the equations pointed to an even deeper, more profound level of insanity at the very heart of it all. At the center, at a radius of 0, Schwarzschild's solution went completely haywire. All the mass of the star, every single particle, was crushed into a point of 0 volume, a place of infinite density, infinite gravity, infinite space-time curvature. This was not just a breakdown of the equations. It was a declaration that the laws of physics themselves shatter. It was the universe divided by 0, a singularity, a place where space and time as we understand them literally end. A true abyss, not just in space, but in our comprehension. When Schwarzschild presented this to the world, when he showed Einstein the ghost that lived inside his beautiful machine, the reaction from the scientific community was one of universal disbelief. Einstein himself was perhaps the most formidable opponent of the idea. He was impressed, certainly by the power of Schwarzschild's mind, but he was repulsed by the physical implications. He wrote papers arguing that nature would always intervene, that the angular momentum of a collapsing star or the internal pressure of its matter would prevent such a catastrophic total collapse into a singularity. These Schwarzschild singularities, as they were called, were a mathematical pathology, a quirk of the idealized, perfectly spherical model. The real universe, messy and complex, would never allow such a perfect storm of gravity to form. It was a monster that must be kept in its mathematical cage. For decades, this remained the prevailing view. These objects, later given names like collapsers or frozen stars, were treated as a fringe idea, a celestial pariah. They were a spooky story that mathematicians might tell each other, but no serious astronomer or physicist believed they were truly out there lurking in the cosmic dark. The universe was thought to be a tamer place, governed by sense and protected from such extremes. The idea of a hole in the fabric of reality, a point of infinite madness from which not even light could escape, seemed more like science fiction than sober scientific prediction. It was an intellectual dead end, an ugly footnote to an otherwise beautiful theory, but a seed of a terrifying question had been planted, a whisper that would not go away. What if Einstein was wrong about being wrong? What if the universe was not as tame as we wanted it to be? What if these mathematical nightmares were real? And that question gave birth to an even more profound challenge, a puzzle that seemed fundamentally unsolvable. If these cosmic prisons do exist, how could we ever hope to prove it? How do you find something that is by its very nature invisible? It emits no light of its own. It reflects no light from others. It is the absolute black, an absence of existence sitting in the middle of the cosmos. You cannot point a telescope at it and see anything at all. Pointing a telescope at a black hole is like trying to see a hole in a piece of black paper in a pitch-black room. It is an endeavor in seeing nothingness. The challenge is almost philosophical. How do you photograph a ghost? How do you capture an image of a literal hole in the universe? Early on, even as they dismissed the idea, theoreticians couldn't help but play with the concept. They sketched out thought experiments, not with computers, but with chalk on blackboards and ink on paper. They began to realize you couldn't see the object itself, but you might be able to see its effects. You could perhaps see its shadow. Not a shadow cast by blocking light, but a far stranger shadow created by its profound gravity. They imagined a disk of superheated gas, a fiery maelstrom of matter, sucked from a nearby star, swirling around the abyss like water circling a drain. They dreamed of seeing the light from stars located directly behind it, their rays bent and warped by the black hole's immense gravity, creating a distorted, ghostly halo, an Einstein ring. They envisioned capturing an image of the event horizon itself, a silhouette of nothingness framed against the brilliant backdrop of the inferno surrounding it. It was a dream born on a battlefield, a flicker of an idea that defied all technological and physical intuition, an ambition to make the invisible visible, to stare into the abyss and force it to yield its secrets. This was the start of a multi-generational quest, a journey to confront the monster that haunted Einstein's equations and to achieve what seemed utterly impossible, to take a picture of the edge of reality itself. But before we could even dream of building the telescope required for such a feat, we first had to find evidence, any evidence at all, that these dark phantoms were more than just a mathematical ghost story. We had to go hunting in the dark. We are faced then with an impasse born from the laws of physics themselves. A cosmic catch-22. To witness the silhouette of a black hole, to see the shadow cast by an event horizon, we need a telescope with a lens not of glass, but of gravity-bending clarity. A telescope with the power to resolve an object so impossibly small in our sky that it would be like trying to spot a single orange left on the surface of the moon. And to build such an instrument, a single dish of metal and wire, you would need to pave over a landmass the size of a continent. It is a demand so audacious, so far beyond the realm of practical engineering, that for decades, the dream of seeing a black hole remained just that, a beautiful but unattainable fantasy, a final frontier that would forever lie beyond our gaze. But what if we were asking the wrong question? What if instead of building an impossibly large mirror, we could synthesize ×1? What if we could trick the universe into giving us the resolution we need, not with a single monolithic structure, but with a network of eyes scattered across the globe, all staring at the same point in the dark. This is the pivot point in our story. It is the moment human ingenuity found a loophole in the tyranny of physics. The answer lies not in building a bigger telescope, but in building a smarter one. A telescope whose true size is not measured in steel, but in the distance between its farthest points. This is the radical, breathtaking principle of interferometry. To understand how it works, you first need to appreciate the fundamental challenge resolution. It's a measure of clarity, of the ability to distinguish two separate points from a single blur. Every telescope from Galileo's spyglass to the Hubble Space Telescope is limited by this. The culprit is a phenomenon called diffraction, a subtle bending of light waves as they pass through an opening, like the aperture of a telescope. This bending smears the light out, setting a hard limit on the smallest detail you can possibly see. There are only two ways to fight back to sharpen your vision. You can observe in shorter wavelengths of light, but the regions around black holes are shrouded in gas and dust that only the longest waves can penetrate. That leaves one option: make your telescope's aperture bigger. The wider your lens or dish, the finer the detail you can resolve. This is why radio astronomers who study the universe in the longest, lowest energy wavelengths of light have always been obsessed with size. Their waves, being much longer than those of visible light, require commensurately larger telescopes to achieve the same clarity. For decades, they built ever more colossal dishes, carving them into valleys and deserts, metal titans straining to hear the faint whispers of the cosmos. But even the largest of these, a 1,000-foot bowl in Arecibo, was laughably inadequate for our quest. To see the shadow of a black hole, we would need a dish not 1,000 feet across, but thousands of miles. We would need a telescope the size of planet Earth. The breakthrough came from reimagining what a telescope truly is. Think of a single large radio dish. A cosmic wave traveling for millions of years finally arrives and washes over it. Different parts of the dish receive the crest of that wave at infinitesimally different times. The dish's electronics are designed to collect all of that information, account for those tiny time delays, and combine the signals into a single coherent point of data. Now, imagine you throw away almost all of the dish. You discard the vast majority of the expensive heavy metal surface, leaving only two small pieces, one at each edge. Those two small antennas would still receive the same cosmic wave. And the difference in the wave's arrival time between them would still contain vital information about the wave's direction and origin. If you could measure that time delay with impossible precision, you could mathematically reconstruct a piece of the information you would have gotten from the full giant dish. You haven't captured as much light, your image will be much fainter, but you have preserved the resolution. You have achieved the clarity of a telescope as large as the distance separating your two small antennas. This is the soul of interferometry. It is a technique for cheating scale, for creating a virtual telescope of planetary proportions out of a carefully coordinated array of smaller, separate instruments. The baseline, the distance between the two most widely separated telescopes in your network, becomes your effective diameter. Suddenly, the Earth itself is no longer an obstacle. It is the foundation upon which your instrument is built. This idea wasn't born overnight. It grew from a century of accumulated wisdom. It began with simple experiments showing that light behaved like a wave, with crests and troughs that could interfere, either amplifying each other in a bright splash or cancelling each other out into darkness. In the mid-20th century, pioneering radio astronomers in England and Australia began linking just two antennas together. They weren't trying to see a black hole. They were simply trying to pinpoint the locations of the first mysterious radio sources in the sky with greater accuracy than ever before. With painstaking effort, they synchronized their instruments and showed that the principle worked. By combining the signals, they created a synthetic instrument that could see with the sharpness of a telescope miles across, revealing that some of these radio smudges were in fact brilliantly compact quasars burning at the dawn of time. This was the birth of Very Long Baseline Interferometry, or VLBI, but scaling it up from a few miles to a few continents presented a cascade of technological hurdles, each more daunting than the last. To combine the light waves from telescopes thousands of miles apart, you don't just need to know the distance between them, you need to know it with a precision smaller than the wavelength of the light you're observing. For the Event Horizon Telescope observing at a wavelength of 1.3 millimeters, this meant the relative positions of antennas in Chile, Hawaii, and Antarctica had to be known to within a fraction of a millimeter. The entire planet had to become a single, rigid optical instrument of unparalleled stability. Then there was the problem of time. The wave from a distant black hole would arrive at a telescope in Spain a few milliseconds before it reached one in Hawaii. To properly combine these signals to perfectly align the cosmic waves crest to crest and trough to trough, that time delay had to be measured with ferocious accuracy. An error of just a trillionth of a second would be enough to scramble the data into meaningless noise. The solution required a timekeeper of almost supernatural stability, the hydrogen maser atomic clock. These are not clocks for telling time in the conventional sense. They are the metronomes of the cosmos, the humming heartbeat of the entire VLBI network. Each one, a closet-sized box of pristine vacuum and excited hydrogen atoms, provides a timing signal so pure, so unwavering, that it would not lose or gain a single second in 100 million years. With one of these clocks at every telescope, the astronomers had a common ultra-precise temporal reference, allowing them to stamp every incoming wiggle of a radio wave with a timestamp of exquisite precision. And there was another, more chaotic adversary, our own atmosphere. As faint radio signals travel through the turbulent, shifting layers of air above each telescope, they are bent and distorted, particularly by water vapor. It's the same effect that makes stars appear to twinkle. For the EHT, this twinkling is a catastrophic source of noise, smearing the very details it seeks to discern. It's like trying to read a book at the bottom of a swimming pool while someone is splashing in the water. The only way to mitigate this was to build the telescopes in the highest, driest places on Earth. The Atacama Desert in Chile, the volcanic peaks of Hawaii, the frozen plateau of Antarctica, the Sierra Nevada mountains in Spain. These locations, hostile to life, are precious windows of clarity portals, where the veil of Earth's atmosphere is at its thinnest, offering the cleanest possible view of the abyss. Even with these solutions, the final challenge was one of sheer data. A single telescope in the array couldn't possibly process the deluge of information it was collecting in real time, and there was no internet connection fast enough to stream petabytes of data from the South Pole or a remote Chilean volcano. The answer was deceptively simple, almost archaic. The torrent of data from each telescope, a flood of information equivalent to thousands of high-definition movies every second, was streamed directly onto enormous stacks of helium-filled hard drives. There was no processing, no analysis. There was only the raw, untamed signal of the universe captured and stored. At the end of an observing run, these hard drives, hundreds of them from each site, would be physically flown by airplane to a central processing facility. This global network of cutting-edge telescopes synchronized by atomic clocks and connected by terabytes of data wasn't just an instrument. It was a logistical miracle, a symphony of coordinated action on a planetary scale. It was the Earth-sized telescope finally realized not as a single dish but as a global collaboration. Now that the how was conceptually solved, the what and where became the paramount questions. Which black holes would we target? The universe is littered with them, but only a select few offered even a remote chance of success. The key metric is angular size, how large the black hole's shadow appears in our sky. This is a delicate trade-off between a black hole's true physical size, which is proportional to its mass and its distance from us. A truly monstrous black hole very far away might appear the same size as a much smaller one that is closer to home. It's like weighing the visual impact of a distant giant sequoia against that of a nearby bonsai tree. After scanning the heavens, after decades of preliminary observations and calculations, the list of potential candidates was whittled down to just two cosmic leviathans that, by a remarkable coincidence of mass and distance, presented the largest apparent event horizons as seen from Earth. These would be our primary targets. The first was the sentimental favourite, the beast in our own backyard, Sagittarius A times pronounced A star. Lurking at the very centre of our Milky Way galaxy, a mere 26,000 light-years from Earth, it is the closest supermassive black hole we know. Its proximity is its greatest gift. With a mass of just over 4 million times that of our Sun, It is by no means the largest black hole in the cosmos, but it is times ours asterisk. For generations, astronomers had tracked the frantic elliptical orbits of stars caught in its grip, watching them whip around an unseen center of gravity, providing the most definitive proof of its existence. Capturing its image felt like a homecoming, a final intimate portrait of the gravitational anchor that holds our entire galaxy together. But Sagittarius A times is a notoriously difficult subject. It is a flickering, tempestuous target. Its relatively small size means that gas and plasma orbit its event horizon with breathtaking speed, completing a full circuit in mere minutes, not days. The glowing ring of matter we hope to see is therefore changing constantly, its hotspots flaring and dying like sparks from a fire. Trying to image Sagittarius A times is like trying to take a long exposure photograph of a hummingbird's wings. The result is destined to be a blur. Compounding the problem, our view towards the galactic center is obscured by a thick screen of intervening gas and dust within the Milky Way's disk, a cosmic fog that scatters and smears the faint signal we are trying to capture. It was a target that was tantalizingly close yet maddeningly volatile, and so the team turned its gaze to the second candidate, a true titan located 55 million light-years away in the heart of the colossal elliptical galaxy Messier 87. The black hole at M87's core is a creature of a different order entirely, weighing in at a staggering 6.5 billion times the mass of our Sun. It is one of the most massive black holes ever discovered. It is a gravitational monster so vast that our entire solar system would fit comfortably inside its event horizon many times over. Its immense distance makes observing it a profound challenge, but its sheer size compensates beautifully. The shadow it casts despite its distance was predicted to be almost the exact same angular size in our sky as that of the much closer, much smaller Sagittarius A asterisk. But M87 offered a crucial advantage: stability. Because it is so much larger, the timescale of events around its horizon is stretched out. Matter takes days, not minutes, to complete an orbit. The glowing ring of plasma is not a flickering candle, but a slowly turning majestic bonfire. It changes, but it changes gracefully, slowly, making it a much more cooperative target for the long observation times required by the EHT. And M87 had another spectacular feature, a calling card that made it an irresistible scientific prize. Blasting out from its core is a colossal jet of energized particles, a celestial blowtorch shooting across space for 5,000 light-years at nearly the speed of light. This jet is one of the most energetic and enigmatic phenomena in the universe, believed to be powered by the black hole's immense rotation and magnetic fields. To see the base of that jet, to witness the exact point where it is launched from the edge of the event horizon, would be to solve a fundamental mystery of astrophysics. So the stage was set, 2 targets each presenting a unique and formidable challenge. In one corner, the hometown champion Sagittarius A, times close, familiar but flickering and shrouded in mist, a test of our ability to see through the fog and capture a moment of fleeting clarity. In the other corner, the distant heavyweight M87, a stable, serene giant, offering a clearer view but testing the limits of our telescope's resolving power against the crushing emptiness of intergalactic space. The strategy was clear. They would observe both. They would point their planetary scale eye first at one, then the other, gathering petabytes of data from each. The technology born from a century of innovation was ready. The global array of telescopes stood poised, a network of silent listeners waiting for a signal from the void. The grand challenge, once a mere fantasy, was about to become an observational reality. All that remained was to unite the planet, to synchronize a world of steel and silicon, and to wait for the Earth to turn, transforming our scattered observatories into a single magnificent lens aimed at the edge of forever. The theory was pristine, a perfect crystalline structure of mathematics built over a century. It told us that an object of infinite gravitational power would leave behind a fingerprint, a dark silhouette, an abyss carved into the very fabric of space-time itself. But a theory, no matter how elegant, remains a ghost in the machine until it is witnessed. And witnessing this ghost required an instrument that did not exist. It demanded an eye the size of a planet, The challenge was so colossal, so fundamentally absurd it could have been dismissed as fantasy. Yet within the global community of radio astronomers, a radical idea began to coalesce. It was an idea born not in a single mind, but in a constellation of conversations. A whisper exchanged over humming computer terminals, a concept sketched on napkins, a notion that grew from a speculative what if into a defiant how can we? What if we didn't need to build a single contiguous dish spanning the Earth? What if instead we could teach the great radio telescopes of the world to see as one? This was the genesis of the Event Horizon Telescope Consortium. It was less an organization and more a scientific crusade, a grand conspiracy of dreamers. A planetary-scale endeavor to orchestrate a moment of cosmic revelation. The first step was not to pour concrete or lay cable, but to build a network of trust. It began with a handful of pioneers led by astronomers like Shep Doeleman. They traversed the globe not as conquerors, but as envoys with an audacious proposition. They asked the stewards of the world's most powerful celestial ears to join their quest, to lend their prized instruments, their teams, their time to a project with no guarantee of success. They were asking entire institutions to gamble on a single fleeting observation, an observation of an object that by its very nature devours all light. To succeed, they had to perfect a technique known as very long baseline interferometry, or VLBI. The principle is as beautiful as it is mind-bending. Imagine two people standing far apart, both listening to the same distant sound. By comparing the precise moment the sound wave reaches each person, you can pinpoint its source. The EHT would do this not with sound, but with the faint radio waves from a black hole's edge, and not with two listeners, but with an entire orchestra of them scattered across the planet. Each telescope in the array would act as a tiny fragment of a much larger virtual mirror. The distance between any two telescopes, the baseline, would define the resolution. The wider the separation, the sharper the vision. To capture the shadow of Sagittarius A times the monster in our own galaxy's heart, they needed baselines that stretched across continents and oceans. They needed to transform the Earth itself into a single light-collecting instrument, a vast terrestrial camera lens aimed at the void. The call went out, and slowly, miraculously, the giants began to answer. The first to join the symphony were the twin dishes of the sub-millimeter array, and nestled beside it the venerable James Clerk Maxwell telescope. They sit atop Mauna Kea in Hawaii, a sacred mountain piercing the Pacific sky. Here at nearly 14,000 feet, the air is thin and breathtakingly dry. You are above a third of the Earth's atmosphere, floating over a sea of clouds. This altitude, a challenge for human lungs, is a paradise for radio astronomy. It is a place where the water vapor that normally blinds us to the universe is swept away, leaving a crystal-clear window into the millimeter wavelength light they needed to collect. These Hawaiian telescopes formed the crucial western anchor of the network, a listening post perched on a volcanic island in the middle of the world's largest ocean. They would be the first to catch the faint whispers from the galactic center each day. Their data would provide a vital piece of the puzzle, a cornerstone of the virtual mirror. Far to the southeast across the equator lay the driest place on Earth, the Atacama Desert in Chile, a landscape so alien it is used to test Mars rovers. Here, in this desolate expanse of rock and dust, humanity built its most ambitious ground-based observatory. This is the Atacama Large Millimeter Submillimeter Array, or ALMA. ALMA is not one telescope, but a breathtaking phalanx of 66 precision antennas. They work in perfect concert, a choreographed army of steel and silicon. When ALMA was brought online, it revolutionized astronomy overnight. Its sensitivity was so profound it was like moving from nearsightedness to microscopic vision. For the EHT, ALMA was the game changer, the heart of the entire operation. It wasn't just another dish. It was a vast collecting area in its own right, a powerful gravitational center for the entire network, capable of hoovering up photons. Its inclusion amplified the sensitivity of the whole array by an order of magnitude. Persuading the international partnership that runs ALMA to join the EHT was a monumental diplomatic achievement. It meant interrupting its own packed scientific schedule to dedicate precious time, to point its 66 eyes in unison with the rest of the world at a single dark spot in the sky. Its agreement to participate elevated the EHT from a bold experiment to a project with a real chance of seeing the unseeable. The network continued to grow node by precious node. In Arizona, the submillimeter telescope on Mount Graham added a critical link in North America. It provided another baseline, another angle, another piece of the celestial photograph. Each new telescope didn't just add its own collecting power, it multiplied the power of all the others. The number of baselines grows exponentially with each new sight. Adding a third telescope to a pair doesn't just add one new baseline, it adds two more. A fourth telescope adds three more, and so on. The complexity and the resolution of the virtual lens grew with every handshake and agreement. From the sun-scorched peaks of the American Southwest, the network leaped across the Atlantic. In the Sierra Nevada mountains of Spain, the IRAM 30-meter telescope became the European anchor. Its gleaming white dish, nestled amongst snowy peaks, would connect a new continent to the effort. It extended the east-west baseline to thousands of miles. Stretching the virtual mirror, sharpening its focus, allowing it to resolve ever finer details. Suddenly, signals were being captured simultaneously in the old world and the new. A planet was beginning to listen with a singular purpose. Further west, rising from the summit of Sierra Negra, a dormant volcano in Mexico, stands the large millimeter telescope Alfonso Serrano. This is a true colossus, the largest single-dish steerable telescope of its kind on the planet. Its massive 50-meter dish is a testament to engineering ambition. Getting this giant to join the EHT was another painstaking process of collaboration. It required new instrumentation, new software, and a dedicated team working at high altitude. Its immense collecting area would provide another massive boost in sensitivity, a powerful central hub in the growing web of observatories. From Hawaii to Arizona, from Chile to Mexico to Spain, the array was formidable. It spanned the northern hemisphere, creating a web of interlocking baselines. But to achieve the ultimate resolution, to get the sharpest image possible, they had to go south. They had to go to the most remote, inhospitable, and extreme location on Earth. They had to go to the South Pole. At the bottom of the world, in a kingdom of perpetual ice, sits the South Pole Telescope. It is a marvel of human resilience operating in conditions that defy imagination. Temperatures here can plummet to 100 degrees below 0 Fahrenheit. For 6 months of the year, the sun never rises, plunging the station into an endless polar night. The staff who winter over are completely isolated from the rest of humanity. No planes can fly in or out. They are more cut off than astronauts on the International Space Station. But this brutal environment is like the Atacama, an astronomer's dream. The South Pole sits on a plateau 2 miles high, and the extreme cold freezes nearly all the water vapor out of the atmosphere. The air above the pole is the most stable and transparent on the planet. It is the clearest possible window to the cosmos. Including the South Pole Telescope in the EHT array was a logistical nightmare, but a scientific necessity. It would provide the longest possible north-south baselines when paired with telescopes in Spain or Hawaii. This was the key to transforming the virtual telescope from a horizontal slit into a round, complete lens. It would allow them to fill in the gaps in the image, to resolve not just a streak but a circle, the shadow of a black hole. Getting the South Pole on board was the final audacious stroke in the construction of this planetary eye. It connected the very top of the world to the very bottom in a single unified vision. Now they had their network, a global chain of observatories poised and waiting. But this chain was worthless if its links could not be synchronized with impossible precision. Every telescope had to record the incoming radio waves at the exact same moment. If the timing was off by even a billionth of a second, the signals would be meaningless. The beautiful, coherent wave patterns would dissolve into a sea of random noise. It would be like trying to create a coherent picture from photographs taken at different times. The result would be a useless blur. How do you synchronize clocks separated by thousands of miles of ocean and rock more accurately than any timekeeping system in history? You can't use GPS. Its signal is distorted by the atmosphere, introducing fatal errors. You can't use the internet. Its delays are too variable. The solution had to be local to each telescope, yet universal to them all. The answer was found inside a box humming quietly in the control room of each observatory, a device that represents one of the pinnacles of human measurement, the hydrogen maser atomic clock. These are not clocks in any conventional sense. They are the metronomes of the universe. They don't measure time by the swing of a pendulum or the vibration of a quartz crystal. They measure it by the fundamental unchanging quantum leap of a hydrogen atom. An electron shifting from one energy state to another, releasing a microwave signal, a pulse that is one of the most stable and reliable frequencies in all of nature. A hydrogen maser is so breathtakingly precise it will not gain or lose a single second over the course of 100 million years. If you had started one running at the moment of the Big Bang, it would only be off by a handful of seconds today. These instruments became the technological soul of the Event Horizon Telescope. One was installed at every participating site, from the balmy slopes of Mauna Kea to the frozen Antarctic plateau. Each clock was a gravitational anchor for the data, a local standard of time so perfect it could be trusted implicitly. Before the observation campaign, each clock was synchronized using portable atomic clocks flown around the world. Once set, they would run independently, their quantum heartbeats holding the entire global experiment in perfect, unwavering rhythm. When the telescope in Chile recorded a photon, the clock marked its arrival time with unimaginable accuracy. Simultaneously, the clock in Spain would do the same. Later, when the data was combined, astronomers could align these timestamps. They could perfectly reconstruct the single vast radio wave that had washed over the Earth, a wave that had traveled for 55 million years from the galaxy M87 to reach them. Without the maser clocks, there would be no Event Horizon Telescope. There would be no picture. There would only be static. With the network built and the clocks ticking in unison, one final gargantuan hurdle remained: the sheer, overwhelming volume of data. Each telescope in the array, when observing, would generate a torrent of information, so much data, in fact, that it would completely dwarf the capacity of the internet. You simply could not stream petabytes of information from the South Pole or the high Atacama. The digital deluge was too great. The solution was surprisingly almost anachronistically physical. The data from each observatory wasn't uploaded, it was recorded onto stacks of specialized helium-filled hard drives. At the end of the observation run, these drives became precious cargo. They held the digital fragments, the raw pixels of the world's first black hole portrait, and they had to be flown by commercial airline and military transport from every remote corner of the globe. Imagine the journey. A box of hard drives from the South Pole waiting for the first flight out after a long polar winter. Another set carefully packaged against the jarring roads down from the Chilean Andes. Discs flown from Hawaii, Spain, Mexico, and Arizona. A global data harvest, a physical pilgrimage of information. All of these technological fossils, imprinted with the faint whisper of an event horizon, were en route to two central locations: the MIT Haystack Observatory in the United States and the Max Planck Institute for Radio Astronomy in Germany. Here, specialized supercomputers called correlators waited. They were the digital looms that would attempt to weave these disparate threads of data from around the world into a single coherent tapestry. But first, all the data had to arrive. This was never just an endeavor of concrete and electronics. At its core, the EHT was a profoundly human story. It was the story of over 200 scientists, engineers, and technicians from 20 countries and 60 institutions. People from different cultures speaking different languages who chose to set aside competition in favor of collaboration. They were united by a single, transcendent, scientific question. They endured sleepless nights working across impossible time zones, an astronomer in Germany troubleshooting with an engineer in Chile via a crackling satellite link. A software developer in Taiwan writing code that would be run by a telescope operator at the South Pole. It was a planetary ballet of coordination managed through endless emails, video calls, and shared documents. A testament to our species' ability to work as one when confronted with a mystery great enough. They were building more than a telescope. They were building a new model for how science could be done. A model based on open collaboration, shared risk, and a collective dream. A United Nations of Science assembled not to prevent conflict but to achieve the impossible, to stare into the eye of the abyss and not blink. By the first week of April 2017, everything was in place. The years of planning, of negotiation, of technological invention and logistical wizardry had all led to this moment. The global network of 8 telescopes stood ready. The atomic clocks were synchronized, their quantum heartbeats pulsing as one across the planet. The data recorders were loaded with fresh hard drives, hungry for the coming flood of information. The teams at each site were on high alert, a nervous electric energy in the air. They were about to attempt something that had never been done before. For 5 precious nights they would have a window, a brief period when their primary target, the supermassive black hole in the galaxy M87, would be visible to every telescope in the network. But their success was utterly dependent on one thing: they could not control the weather. Not just the weather in one location, but the weather across the entire globe. A storm over the mountains in Spain, a blizzard at the South Pole, or even just high winds in Hawaii could cripple a vital node. It could blind a piece of their virtual eye, ruining the observation for everyone. In control rooms across the world, scientists anxiously watched meteorological charts. They were tracking weather fronts with the same intensity they tracked celestial objects. The fate of this multi-decade, multi-million-dollar quest rested on clouds and air pressure. The tension was palpable. All the pieces were on the board. All the preparations were made. The planet had been wired into a listening device of unprecedented scale. Now all they could do was wait for clear skies and for the command to be given. The command to open the aperture of a telescope the size of the Earth, and for the first time in human history to try and see the edge of forever. The telescopes fall silent. Around the globe, a coordinated campaign of cosmic eavesdropping concludes, and the vast Earth-sized eye we assembled closes. The upward journey, the ambitious act of reaching out across 55 million light-years to touch the edge of a black hole, is over. But here in the quiet aftermath of that digital gaze, the most arduous part of our odyssey has only just begun. The photons have been caught, the signals are recorded. Now begins the downward path, a descent into a computational abyss so profound it would test the limits of our technology and our ingenuity. For we have not captured a picture, we have captured an incomprehensible storm of data, a chaotic whisper from the void, and locked within it we hope is the ghost of an image. The challenge has transformed from one of astronomy to one of archaeology. We must now sift through a digital ruin, searching for the fossilized light of a monster. The treasure we seek is not stored in the cloud or transmitted through fiber optic cables. It is far too vast, too monumental for that. Instead, it is housed in hundreds of helium-filled hard drives, precious metal casings that hold the most valuable scientific data ever collected. To understand the scale, you must abandon all conventional measures of information. The total volume exceeded 5 petabytes, 5,000 trillion bytes. If this were a musical recording, it would play continuously for over 40,000 years. If it were a library of books, it would contain the text of every volume ever written 50 times over. Each drive is a time capsule holding not just the faint signal from Messier 87's core, but also a precise atomic clock-stamped record of the exact moment each radio wave arrived at its destination. This timing, a relentless drumbeat marking the passage of nanoseconds, is the crucial key that will allow us to unlock everything that follows. These drives, now brimming with potential discovery, became the most precious cargo on Earth. They were carefully removed from their sterile high-altitude homes and prepared for a journey not through space but across the planet's surface. They were loaded onto commercial airliners, unassuming passengers in transit holding secrets of cosmic gravity in their magnetic platters. This leg of the journey was fraught with a unique terrestrial anxiety. A single lost crate, a damaged drive, a customs delay could create a permanent blind spot in our virtual telescope, a wound in the data from which we might never recover. Flights were tracked with nervous precision as this digital cargo converged on 2 sanctums of computation on opposite sides of the Atlantic: the Max Planck Institute for Radio Astronomy in Bonn, Germany, and the MIT Haystack Observatory in Pamialiti, Massachusetts in the United States. These facilities housed the computational engines powerful enough to begin the first stage of our alchemical task, the correlators. Here, within climate-controlled rooms, filled with the hum of immense processing clusters, the physical data began its metamorphosis into a coherent whole. A correlator is a very special kind of supercomputer, a digital heart designed for one purpose: to take the disparate, independent streams of data from each telescope and weave them together. You can imagine it like this picture: a global orchestra with each musician playing their part in isolation, unable to hear anyone else. Each one records their performance with their own microphone and their own stopwatch. The correlator is the master conductor who takes these dozens of separate recordings and, using the stopwatch timings, aligns every single note with perfect, unbelievable precision. It slides each track forward or backward by infinitesimally small amounts until the cacophony begins to resolve into a symphony. The notes in our case are the crests and troughs of radio waves, and the precision required is on the order of picoseconds, trillionths of a second. This is a temporal alignment so fine that it accounts for the Earth's rotation, the minute flexing of its crust, the exact path the signal took through the wisps of our atmosphere, and even the subtle gravitational time dilation predicted by Einstein's own theories. For months, these machines churned their processors, running at full capacity, executing quadrillions of calculations every second. The task was Herculean. The correlator had to compare the signal from every telescope with the signal from every other telescope for every single moment of the observation. This creates a matrix of connections, a web of what astronomers call visibilities. Each visibility represents the data from a pair of telescopes, forming one unique baseline of our Earth-sized array. The more baselines, the more detail we can potentially resolve. The correlator's job was to find the faint, common signal from the black hole buried beneath the overwhelming noise of local interference and the telescope's own electronics. It was a process of finding a single, coherent hum amidst a billion roaring distractions. Slowly, painstakingly, the raw, independent recordings were synchronized, their clocks aligned, and their data streams combined. After this monumental effort, the 5 petabytes of raw recordings were condensed into a more manageable, yet still enormous 20 terabytes of correlated data. The orchestra was now playing in time, but the music was still a chaotic, distorted mess. We had created the raw material, but the sculpture was still trapped inside the stone. Now, the true challenge revealed itself: a hydra of problems that stood between our correlated data and a final image. The first and most fundamental hurdle is the brutal reality of what our virtual telescope actually is. We call it an Earth-sized telescope, but this is a grand and somewhat misleading poetry. In truth, it is an Earth-sized mirror that is almost entirely black, with only a handful of tiny, polished patches corresponding to the locations of our radio dishes. We have not sampled the full, continuous wavefront of light from the black hole. We have only captured tiny, isolated fragments of it. This is what we call a sparse array. Imagine trying to recognize a person's face by looking only through 8 tiny pinholes in a piece of cardboard. You might see a glint from an eye, the curve of a cheek, a part of a smile, but you would have to infer the rest. Our task was a cosmic version of this. We had to take the information from these few scattered points of data and reconstruct a plausible, physically consistent image of the entire source. The vast empty spaces between our telescopes were gaps in our knowledge, voids of information that no amount of processing could ever truly fill. Compounding this problem was our planet's own atmosphere, the very air we breathe. To us, it is transparent, a window to the heavens. But to the specific millimeter wavelength radio waves we were observing, the atmosphere is a turbulent, shimmering veil. The primary culprit is water vapor. Pockets of moisture drift across the sky, bending, scattering, and absorbing the faint radio signals on their long journey to the telescope dishes. Looking through the atmosphere at these wavelengths is like trying to see the bottom of a river through its swirling currents. The image is constantly distorted, its light dimmed and twisted. This atmospheric corruption is unique for each telescope at each moment in time, creating a separate chaotic distortion for every single one of our data streams. Before we could even begin to think about what the black hole looked like, we had to first model and subtract the effect of every cloud, every wisp of humidity, every pocket of turbulence that drifted over every telescope for every second of CROS. The week-long observation. It was a calibration nightmare of planetary proportions, requiring sophisticated weather modeling and complex mathematical corrections to effectively dry the sky and stabilize our view. Then came the instruments themselves. No two telescopes are identical. Each one has its own electronic personality, its own unique set of imperfections, gains, and sensitivities that color the data it collects. The receivers, the amplifiers, the digital recorders, they all impart a subtle instrumental fingerprint onto the celestial signal. To build a coherent picture, we had to understand the precise behavior of each component in the global array and meticulously calibrate it out. It was akin to realizing that in our global orchestra, one violinist's instrument was tuned slightly sharp, a cellist's bow was subtly frayed, and a flutist had a unique breathy timbre. To hear the pure music of the cosmos, we first had to account for the unique, imperfect voice of every single instrument we used to listen to it. This process of calibration, of removing both atmospheric and instrumental noise, took months of painstaking iterative work. Scientists would apply a correction check, the results, find a new, more subtle error, and begin again. It was a slow, deliberate process of peeling away layers of contamination to get to the pristine signal hidden deep within. With the data correlated and calibrated as best as possible, we stood at the final precipice. We had a vast set of visibilities, the noisy, incomplete measurements from our sparse array, and we had a monumental question: what image, when viewed by our virtual telescope, would produce the exact data we collected? This is what is known as an inverse problem, and it is devilishly difficult. There isn't one single perfect answer. Because of the gaps in our array, an infinite number of possible images could in theory be consistent with our data. So how do we choose the right one? How do we convince ourselves that what we are seeing is the black hole and not some phantom, some artifact of our own complex processing? The answer was to not trust any single method or any single team. The Event Horizon Telescope collaboration made a brilliant, critically important decision. They split the imaging teams into 4 distinct, independent groups. Each team was given the exact same calibrated data, but they were to use completely different imaging algorithms and software developed over years of research to reconstruct a picture. They were forbidden from communicating with each other about their results. It was a blind test on a cosmic scale designed to protect the most important scientific discovery from the most dangerous of all contaminants, human bias. We are pattern-seeking creatures. If a scientist expects to see a ring, they might subconsciously tweak their parameters until a ring appears. By having 4 teams working in total isolation, the collaboration ensured that if a consistent image did emerge, it would be a feature of the data itself, not the desire of the scientists. The algorithms these teams employed represent the true cutting edge of computational imaging. They are not simply connecting the dots. They are sophisticated pieces of software that use principles of statistical inference and machine learning to find the most plausible image. One of the leading techniques, known as regularized maximum likelihood, or RML, works by creating millions of random possible images of the sky. For each synthetic image, the algorithm simulates what our Earth-sized telescope times would have seen times if that image were the real thing. It then compares this simulated data to our actual measured data. The image that produces the closest match is considered a better fit, but the algorithm doesn't just search for a good fit, it also searches for simplicity. It penalizes images that are overly complex or contain sharp, unnatural features that are not explicitly required by the data. It favors the smoothest, simplest image that can explain what we saw. It is a mathematical expression of Occam's razor, a computational artist guided by the laws of physics trying to paint a picture with the fewest possible brushstrokes. For months on end in Bonn, in Massachusetts, in Arizona, and in Cambridge, the teams worked. They fed the data into their powerful computer clusters and waited. The process was not automatic. It required constant human intervention, a deep understanding of the software's assumptions, and a cautious interpretation of the results. The algorithms would run for days, sometimes weeks, exploring the vast space of possible images, slowly converging on a solution. The scientists watched as from the sea of statistical noise, a structure began to tentatively emerge. It wasn't a sudden flash of insight, it was a gradual, painstaking materialization. On computer screens across the world, pixels began to arrange themselves. The chaotic static started to resolve, and in the silence of their isolated labs, the teams all began to see the same impossible, extraordinary thing. It was a ring, a lopsided, asymmetric ring of blazing light, and in its center, a profound and unmistakable darkness. This was not a crisp photographic circle. It was a fuzzy, ethereal halo, brighter on one side than the other, just as theoretical models predicted it should be. The brighter region was the side of the accretion disk, spinning towards us, its light amplified and blue shifted by the extreme velocity and gravitational lensing. The dimmer side was the material spinning away from us, and the dark patch in the middle, that was the prize. That was the black hole's shadow. It was the direct visual evidence of the event horizon, the point of no return silhouetted against the incandescent plasma swirling around it. This was the abyss made visible, a circle of pure blackness on the sky, a place where space-time itself comes to an end. The sheer emotional gravity of these moments cannot be overstated. For the individual scientists, seeing this structure coalesce on their screens was the culmination of a decade of work, a lifetime of dreaming. Yet they could not share their elation. They could not pick up the phone and ask the other teams, "Are you seeing this too?" They had to sit with their discovery, with this epochal image, in disciplined silence, meticulously validating every step of their analysis, running every conceivable test to try and make it go away. They had to prove to themselves beyond any shadow of a doubt that this ring and this shadow were not a phantom of their software, but a true message from the universe. They were the first human beings in history to look upon the face of an event horizon, yet they had to carry that secret alone, waiting for the day they would all come together. The symphony had been assembled from its scattered parts. A strange, powerful, and utterly new music was playing, and now all that was left was for the conductors to finally compare their scores, and so the vigil began. Across the globe, the digital deluge had finally settled. Petabytes of raw, incoherent noise, the faint whispers of a cosmic titan, were now imprisoned in silicon, waiting for the magicians. The great journey was over. The telescope's eye had closed. But a far more difficult journey, a voyage through an ocean of pure data, was only just beginning. This was not a photograph waiting to be developed in a dark room with chemicals. It was a ghost, a phantom, scrambled across thousands of drives, its form so faint, so buried in the static of the cosmos and our own technology, that it might never be coaxed into the light. The challenge was no longer about engineering, but about belief. Belief in the algorithms, belief in the team, and a fundamental belief that a coherent truth lay hidden in the chaos. To protect this truth from the most human of flaws, bias, the Event Horizon Telescope collaboration made a radical decision. They would split their world-class imaging experts into 4 separate isolated teams. Housed in different institutions using different computational methods, these groups were forbidden from communicating. A digital wall of silence was erected. They were 4 separate expeditions sent into the same uncharted territory, each with a different map, hoping to find the same legendary beast. This was the very soul of the scientific method, weaponized against wishful thinking. If one team saw a ring, it could be an artifact, a flaw in their code. But if 4 independent teams using wildly different techniques all returned from their solitary quests with a picture of the same thing, that would be reality. That would be irrefutable. Imagine the pressure inside those cloistered rooms. The months stretch on bleeding from winter into the spring of 2018. You are there in a room illuminated only by the glow of monitors, the air thick with the hum of processors and the scent of stale coffee. The walls are covered in whiteboards, a chaotic tapestry of equations, flowcharts and diagrams, the desperate scrawlings of minds at their absolute limit. One team, led by Andrew Chale, employs a traditional method called CLEAN, a trusted algorithm in radio astronomy for decades, painstakingly cleaning the image, pixel by pixel, like an archaeologist with a fine brush. Another, featuring the work of graduate student Katie Booman, uses a radical new system, a form of computational imaging that asks not what does the picture look like, but rather what are the simplest structures that could possibly explain this data. It was a philosophical difference in approach. One sought to chisel the statue from the marble, the other to let the marble reveal the statue hidden within. Days blur into nights. Progress is measured not in breakthroughs, but in the slow, agonizing elimination of errors. A single miscalibrated timestamp from one telescope could corrupt everything. A subtle atmospheric distortion that wasn't perfectly modeled could create phantom structures, tricking them into seeing a galaxy of illusions. They ran simulations, creating fake data of known objects, quasars, distant galaxies, and feeding it to their algorithms to see if they could reconstruct the known truth. Sometimes they could, sometimes maddeningly they could not. It was a grueling, spirit-sapping process of refinement. Every line of code was scrutinized. Every assumption was questioned, attacked, and defended. They were not merely processing data. They were battling their own blind spots, their own hopes of what they wished to find. The shadow of M87 times was not their only adversary. The shadow of human error loomed just as large. Then, slowly, tortuously, after months of digital silence, the first ghosts began to appear on their screens. They were not clear. They were not beautiful. They were smudged, blurry apparitions like a watercolor painting left out in the rain. A faint asymmetry here, a hint of a brightness deficit there. It was like trying to recognize a face in a dense fog. Was that a feature, or was it just noise, a cruel trick of the numbers? In one room, a fuzzy blob emerges. They refine the parameters, run the algorithm again for another 48 hours. The blob seems to resolve just slightly into a lopsided crescent. A surge of adrenaline quickly tempered by professional skepticism. Could this be it? Or is the code simply producing what it was designed to find? They would tear it apart, try to break it, force it to produce anything else. The crescent would resist stubbornly, reappearing in the data, a faint, persistent signal against an overwhelming tide of randomness. In another room, hundreds of miles away, a different team stares at their own screen. Their different method, their different philosophy has produced its own version of the ghost. It's not identical, but it shares a familial resemblance. A ring-like structure brighter on one side with a dark patch in the middle. They too are seized by a mixture of exhilaration and terror. The temptation to call someone to break the protocol must have been immense. To whisper a single question into the void, "What are you seeing?" but the vow of silence held. Each team had to walk the final mile of their journey alone, carrying their fragile, unverified discovery to the appointed rendezvous, unsure if they were carrying a priceless treasure or a worthless illusion. The fate of a billion-dollar project of decades of work rested on the hope that when those doors finally opened, their ghosts would look the same. It was a gamble on the very nature of reality itself that there was one singular objective truth waiting at the center of M87, a truth so powerful it could be independently discovered. The day of convergence finally arrived in the summer of 2018. Black Hole Pizza Day, they called it, an attempt at levity to mask the almost unbearable tension. The teams gathered at the Black Hole Initiative at Harvard. There were no grand pronouncements, no ceremony, just a simple room, a projector, and the quiet shuffling of people finding their seats. The air was electric. You could feel the collective pulse of the room, the unspoken question hanging over every single person. Did we do it, or did we all fail, just in our own unique ways? The leaders of the 4 teams sat at the front, laptops open. The protocol was simple. One by one, they would project their final best image. No preamble, no excuses, just the result. The first team goes up. A slide appears on the screen. On it, a blurry, uncertain ring of light. It's smeared a little misshapen, but it's undeniably there. A distinct circle of emission surrounding a dark interior. A cautious, intellectual curiosity ripples through the audience. It's interesting, it's promising, but it is not yet proof. The presenter says little, their face a mask of neutrality. The second team is called "A New Slide Replaces the First." A different algorithm, a different set of choices, a different path through the data. And yet, there it is again. The ring. This one is sharper in some places, blurrier in others, but the fundamental morphology is identical. The same size. The same orientation on the sky. The same dark central region. A murmur spreads through the room, now a wave of palpable shock. It's working. The feeling is no longer just curiosity, it's the dawn of belief. The third team presents. Their image flashes onto the screen. And again, the ring. Unmistakable, indisputable, It's like seeing the same person in 3 different photographs taken by 3 different cameras. Each has its own quirks, its own lighting, but the identity of the person is absolute. Now the 4th team, Katie Booman's team. Their image was generated by the most novel methods, the ones that made the fewest assumptions about the source. This was the ultimate test. Her slide clicks into place. A profound silence falls over the room. On the screen is a blazing golden-orange ring, clearer, sharper, and more defined than the others, but it is the same object, the exact same object. The same cosmic smoke ring, a perfect shadow cast across space-time brighter on the bottom, just as the theories of light bending in a spinning gravity well predicted. It was all there. For a moment, nobody moved, nobody spoke. The shared image on the screen was more than just data. It was a cosmic Rosetta Stone, the key to a script written in the language of gravity itself. It was the culmination of a century of thought, from Einstein's first inkling on a piece of paper to this luminous, terrifying and beautiful circle hanging in the quiet room. And then the spell broke. The silence shattered, replaced by a wave of pure, unadulterated emotion. A collective gasp. Laughter. People turning to each other, eyes wide with disbelief. And then tears. Scientists who had spent their entire careers in a world of sober, objective detachment were openly weeping. Tears of relief after years of carrying an impossible burden. Tears of joy at witnessing something no human had ever seen. And tears of awe at the sheer profound beauty of the universe they had uncovered. Shep Doleman, the project's director, felt the history of the moment wash over him. "We got it," he said, his voice thick with emotion. "We have seen the gates of hell at the edge of space and time." In that room on that day, humanity for the very first time knew what a black hole really looked like. The work that followed was one of verification and refinement. The teams, now united, began the meticulous process of combining their results, cross-validating every step to produce a single canonical photograph. They had to be certain the world would be watching. They debated everything from the statistical significance of every pixel to the very color palette used to represent the radio waves. They chose orange and yellow, the colors of fire, not because the ring is literally that color, it's a radio object with no visible color at all, but to convey the immense energy, the incandescent violence of the matter being heated to billions. Tear of degrees as it screams towards the point of no return. It was a choice born of art as much as science, an attempt to translate the physics into a language everyone could understand, the language of awe. They prepared in secret a global conspiracy of knowledge, planning 6 simultaneous press conferences across the planet: Brussels, Santiago, Shanghai, Taipei, Tokyo, and Washington, D.C. The announcement was coordinated to the second, a testament to the collaboration that had made the discovery possible. The scientific papers were written, peer-reviewed in record time, and held under the strictest embargo in recent scientific history. A secret was being held for the entire world. April 10th, 2019. In press rooms around the globe, an expectant hush falls. Journalists, scientists, and the public have gathered for an announcement that was teased with only the most cryptic of promises, a groundbreaking result from the Event Horizon telescope. Everyone knew what it might be. But to know and to see are 2 profoundly different things. On a stage in Washington, Shep Doleman steps to the podium. He speaks of a telescope as wide as the world. He speaks of a quest to see the unseeable. He speaks of Einstein, of a theory of gravity that predicted these bizarre, invisible monsters, these points of infinite density where the universe itself breaks down. The anticipation builds a palpable force in the room and for millions watching online. We are with them in that moment, holding our collective breath. We have journeyed with this team across frozen deserts and volcanic peaks. We have felt the frustration of failed observations and the anxiety of processing. And now we wait for the final revelation. We are here today to tell you about a project that has lasted for decades, Doleman says. We have generated an image of a black hole. His voice cracks slightly. This is it. And then it appears. Projected onto giant screens across the world simultaneously. A perfect glowing ring of fire suspended in the blackness of space. A halo of light surrounding a pit of absolute nothing. the shadow of Messier 87 asterisk. 55 million light-years away, an object of unimaginable power now captured, resolved and presented for all of humanity to see. The room erupts, not just with applause but with a sound of pure astonishment. The clicking of 1,000 cameras creates a sound like thunder, but for a few seconds the dominant sound is the human gasp of wonder. It's real. The monster at the heart of the galaxy is real, and it looks exactly, precisely, hauntingly, like the theories predicted. It is a perfect circle not because it is a simple object, but because it is warping the very fabric of space-time into a perfect lens. We are not seeing the event horizon itself. We are seeing its silhouette backlit by the tortured plasma swirling around it. It is a photograph of gravity's autograph. In that instant, the image was seared into our collective consciousness. It became an icon, a symbol not only of scientific achievement but of our relentless, unyielding curiosity. It was proof that there is no mystery so profound that we will not try to solve it, no darkness so absolute that we will not try to build a light to see it. The image is a validation of Albert Einstein, a man who died 64 years earlier, never knowing for certain if his strangest, most disturbing prediction was true. On the screen we see his equations of general relativity playing out not as abstract mathematics but as a physical fiery reality. The lopsided brightness of the ring is the final triumphant confirmation. The side of the disk spinning towards us is blue shifted by relativistic effects, making it appear brighter. The side spinning away is red shifted, making it dimmer. It's an effect straight from the pages of his theory, now visible across 55 million years. Look at that image. Look at the dark patch in the center. That is the shadow. That is the abyss. It is a region of space-time 40 billion kilometers across, wider than our entire solar system. Within that darkness, 6.5 billion times the mass of our sun has been crushed into a point of infinite density. It is a place from which nothing, not even light, can escape. For the first time in history, you are not imagining it. You are seeing it. You are staring into the void. And in that moment of revelation, we see not just the awesome and terrifying power of the universe, but the incredible, hopeful power of human collaboration. Hundreds of scientists from dozens of countries speaking different languages, working together for a decade with a single shared impossible goal: to take a picture of the invisible. And they did it. They gave us a new icon of exploration. They gave us a new window into the fundamental nature of reality. But as the world celebrated this monumental photograph, the scientists of the EHT knew this was not an ending. It was a beginning. For now that we have finally seen the shadow of a giant, an entirely new set of questions arises. What secrets are written in the precise shape of that ring? What can it tell us about the mangled physics of the event horizon itself? And what other monsters are still out there waiting in the dark for their portrait to be taken undefined? And so, the abyss stared back. Not with an eye, but with a ring of captured light, an incandescent halo branding the edge of space-time itself. For a moment, the world held its breath, united in the shared experience of witnessing the impossible made manifest. But once that initial global gasp of wonder subsided, a deeper realization began to dawn within the halls of science. This image, this ghost of a celestial monster 55 million light-years away, was far more than a breathtaking portrait. It was a crucible. It was the ultimate unforgiving proving ground for our most profound theory of reality, a place where the laws of physics are pushed to their absolute breaking point. For a century, Albert Einstein's general theory of relativity had been our guide to the cosmos, predicting the subtle warp of starlight and the gentle ticking of clocks in orbit. It had performed flawlessly in the gentle realm of our solar system, but M87 times was a different beast entirely. This was the gravitational deep end, a domain of such extreme violence and warped geometry that until now we could only explore it through the pristine abstract language of mathematics. The equations told us what should be there. They painted a picture of a photon ring, a perfect circle of light comprised of photons trapped in frantic last-ditch orbits around the black hole's edge. They predicted a shadow, a region of darkness cast not by obstruction but by the gravitational capture of light itself. The theory dictated the precise size of this shadow, a dimension governed by nothing more than the black hole's mass and the cosmic speed limit. When the international team of scientists finally measured the diameter of that glowing ring, a collective sigh of vindication echoed through the community. The number matched. Within the tight constraints of their observations, the shadow of M87 times was exactly the size Einstein's century-old equations said it should be. Had it been larger or smaller, it would have meant our understanding of gravity, the very foundation of modern cosmology, was incomplete. It would have hinted at new physics, exotic forces lurking in the dark. But the measurement held firm, a stunning testament to a theory conceived in a mind that could never have dreamed of seeing its ultimate prediction confirmed with such spectacular finality. The universe in its most extreme laboratory played by the rules he had uncovered. This was not just a passing grade. It was a triumphant validation in an arena where failure meant rewriting the book on reality. The image also whispered secrets about the nature of the black hole itself. A key tenet known as the no-hair theorem posits that black holes are terrifyingly simple objects. Once formed, they are defined by only three properties: their mass, their spin, and their electric charge. All other complexities of the star that collapse to form them, its chemical composition, its magnetic fields, are swallowed and erased forever. This simplicity should manifest as a near-perfectly circular shadow. And as astronomers traced the contours of that distant ring of fire, they found precisely that. A shape of profound, almost unnerving geometric purity, as if drawn by a cosmic compass. It was another victory for relativity, another piece of the puzzle falling into its predicted place. This was more than just seeing a black hole. It was understanding it, measuring its fundamental properties from an impossible distance. We were no longer just observers of the cosmos. We were becoming cosmic surveyors, using light from the dawn of time collected by a telescope the size of our planet to weigh a monster in the heart of another galaxy. The achievement was monumental, a closing of a chapter that began with a thought experiment 100 years ago. Yet in that same moment of confirmation, 1,000 new questions were born, because the image held more than just the silent, perfect darkness of the shadow. It held the story of the light itself. The ring was not uniform. One side shone with a fierce, brilliant intensity, a blazing crescent that outshone its opposite flank. This asymmetry was not an imperfection in the image. It was the key. It was a Doppler-beamed fingerprint, the first direct visual evidence of the maelstrom of matter we call an accretion disk, spinning at unimaginable speeds. The brighter side was the material hurtling towards you, its light blue shifted and intensified by its relativistic velocity. The dimmer side was the material racing away from you, its light stretched and reddened into obscurity. For the first time, we could see the direction of the black hole's spin imprinted on the flow of its final meal. We were witnessing the raw, chaotic engine of an active galactic nucleus in operation. This swirling disk of superheated plasma, hotter than the core of 1,000 suns, is the source of the black hole's power and its terrifying reputation. It is a place of unfathomable friction and magnetic turbulence, where entire stars are shredded into streams of incandescent gas. From this cosmic grinder, we knew that some black holes, M87 times among them, were capable of launching one of the most astonishing phenomena in the universe, a relativistic jet. A colossal particle beam, a celestial blowtorch, longer than the galaxy is wide, ejected from the poles of the black hole at over 99.9% the speed of light. For decades, the link between the accretion disk and the launching of this jet was theoretical, a model built on supercomputer simulations. The EHT image transformed theory into observation. By mapping the magnetic field swirling within that glowing ring, scientists could finally see the structure needed to power the jet. They saw the fields being twisted and amplified by the spinning spacetime, coiled like a cosmic dynamo, providing the immense energy required to grab matter from the disk and violently hurl it out into the intergalactic void. We were seeing the base of the jet, the launch pad, the very point where the monster feeds and unleashes its incredible power. It was like finally getting a clear view of a hurricane's eye, and in doing so, finally understanding the mechanics of the storm itself. The triumph at M87 times, however, was always intended as a beginning, a magnificent dress rehearsal for an even more audacious target, a target that is in cosmic terms right in our own backyard. For at the very heart of our own Milky Way galaxy, 27000 light-years away, lurks our own supermassive black hole, Sagittarius A *. This is the gravitational anchor of our home, the silent puppet master, around which every star you see in the night sky, including our own sun, dutifully orbits. To photograph it has been the EHT's ultimate ambition, a family portrait of the beast that holds our galaxy together. But SCURE A times presents a profoundly different and more maddening set of challenges. Where M87 times is a heavyweight champion at 6.5 billion solar masses, SCURE A times is a nimble welterweight a mere 4 million times the mass of our Sun. This dramatic difference in scale changes everything. A smaller black hole means a much smaller event horizon. Matter orbits M87 times over the course of days or weeks, giving the EHT a relatively static target to observe over a single night. But at SCURE A times, the orbital dance is frantic. Matter completes a full circuit in a matter of minutes, not days. This means the view is never still. The hot spots in the accretion disk, the very features the telescope needs to resolve, are flickering and swirling on a timescale faster than the EHT can effectively capture. It is the difference between taking a photograph of a mountain and trying to capture a clear image of a hummingbird's wings in mid-flight using a long exposure. The image is constantly blurred by the object's own dizzying motion, and as if this inherent turbulence weren't enough, our view is obscured. To peer into the heart of the Milky Way is to look through the thickest, densest regions of our galaxy's central plane. We must stare through tens of thousands of light-years of interstellar dust and charged gas, a cosmic fog that scatters and distorts the radio waves the EHT is designed to detect. This effect, known as interstellar scattering, is like trying to view a distant lighthouse through a sheet of frosted glass. The image is smeared, its precious details warped before they ever reach our telescopes. Overcoming these twin obstacles, the frantic speed and the galactic fog, has required an entirely new level of ingenuity. Years have been spent developing sophisticated new algorithms to de-blur the cosmic static and to account for the rapid motion, attempting to reconstruct a coherent image from a flickering, chaotic signal. Capturing Sagittarius A times is therefore not just a repeat performance. It is a far more delicate and demanding piece of scientific artistry. It is the challenge that will push the Event Horizon Telescope to its absolute limit, a test of whether we can truly resolve the gravitational heart of our own home to see the anchor to which we are all bound. But even as the team works to unveil this next great portrait, their eyes are already set on a horizon beyond still images. They are dreaming of the next generation of discovery, of moving from photography to cinematography. This dream is the Next Generation Event Horizon Telescope, the NGEHT. It is a bold, ambitious plan to elevate this global array from a pioneering instrument into a permanent, high-fidelity cosmic observatory. The plan involves more than doubling the number of radio dishes in the network, adding new sites in more remote locations across the globe to sharpen the resolution. It also involves observing at multiple radio frequencies simultaneously, allowing astronomers to cut through the interstellar fog with even greater clarity, and to create multi-layered, almost three-dimensional maps of the black hole environment. This technological leap forward will transform the blurry rings of today into crisp, detailed portraits. We will move beyond simply seeing the shadow to studying its intricate structure, looking for subtle deformations that could betray secrets of the black hole's internal spin, or even hint at exotic physics beyond Einstein. But the most revolutionary promise of the NGEHT is the one that captures the imagination most fiercely: the creation of movies. With more telescopes and greater sensitivity, the NGEHT will be able to collect data fast enough to capture the dynamic motion around a black hole in near real time. Imagine it. We will no longer be limited to a single static snapshot averaged over a long night of observation. We will witness the celestial mechanics as they happen. We will be able to watch frame by staggering frame as a blob of superheated plasma is torn from the accretion disk and begins its final fatal plunge towards the event horizon. We could see the shadow of the black hole itself appear to wobble and shimmer as the orbiting matter tugs on the space-time around it. We may even see the very moment of genesis for a relativistic jet, witnessing the magnetic fields twist themselves into a colossal cosmic cannon and fire a bolt of matter across the galaxy. This would be a paradigm shift in our study of the universe. It is the difference between looking at a photograph of a waterfall and being able to watch the water cascade over the edge, to see the eddies and currents, to truly feel its power and motion. These movies would provide a torrent of data allowing us to test general relativity not just in a static state but in a dynamic, evolving environment. We could finally answer long-standing questions about how black holes accrete matter, how they power their jets, and how these colossal engines influence the evolution of their host galaxies over billions of years. We would be watching gravity at work in its most elemental and powerful form. This is the ultimate goal, to move from seeing the unseeable to understanding the unimaginable. The first image of a black hole was a watershed moment, a point in our history when a theoretical abstraction became a tangible reality. It was a triumph of human collaboration, a testament to our relentless curiosity, a single image that required a planetary-scale effort to create. It gave us a new perspective on our place in the universe, revealing the sheer scale and power of the objects that lurk in the cosmic darkness. It has forever changed the night sky. When you look up now, you know that hidden in the hearts of those distant glittering galaxies are monsters of impossible gravity, bending light-swallowing stars, and shaping the cosmos on a scale we are only just beginning to comprehend. The Event Horizon Telescope has in essence given humanity a new sense. Not sight in the traditional way, but a way to perceive the very structure of space-time, to see the shape of gravity itself. It is a sense that will only grow sharper, more refined, and more powerful in the decades to come. The first picture was the end of a century-long quest, but it was also the first word in a new cosmic language we are just now learning to speak. A language that will one day allow us to read the most violent, most mysterious, and most fundamental stories the universe has to tell. The abyss stared back, and in its reflection, we saw not an end, but an infinite beginning.